Welcome back. Section 1.5, infinite limits. So what we're going to look at today is having a limit, or taking a limit, and ending up with an infinity or a negative infinity as our solution or our answer. And what it's going to do is going to allow us to define a vertical asymptote through the eyes of calculus and give you a more precise sort of justification for a vertical asymptote occurring. So we say a vertical asymptote occurs at x equals c when the function approaches a positive or negative infinity as x approaches c from the left or to the right. So what does that kind of look like? And hopefully we remember what a vertical asymptote looks like. But through the eyes of calculus, maybe we have a branch that comes in like this, and then maybe another branch that comes in like this. And we'll define this vertical line here as x equals c. So here, from the left side, or the negative side of the function, the negative branch is coming to an infinity. Whereas from the positive side, or the right side, it goes to a negative infinity. So we would say the limit here, as x approaches c, of f of x from the negative side, so we show that little minus sign, is going to equal infinity. And the limit as x approaches c from the positive side of f of x, so from this side, is going to be a negative infinity. So this would be our justification showing that c is a vertical asymptote. Because we know as we take the limit from the positive and negative side, we end up with an infinity or a negative infinity. We could see that these are both infinity or both negative infinity, which is going to allow us to show that it's a vertical asymptote as well. So in order to find these vertical asymptotes and to be able to justify them, we're going to first remove all the holes. And that's going to remove our removable discontinuity. Remember, removable discontinuity is just a hole that we can take out, and then it would be a continuous function. Then we set the denominator equal to 0. And then to prove or to justify that, we're going to show that the limits from the positive or negative side go to one of the infinities. So it shouldn't be too miserable work in here to see this today. So the first thing we're going to do, example 1 asks us to find and then to prove or to justify that we have a vertical asymptote. So we don't have a holes because we don't have a common factor on top and bottom. So we're going to set that bottom equal to 0, that denominator. Solving for x, we get x equals 5. Now what we want to do is we want to justify it. So we found it. We believe we found it. Now we want to prove that that's happening. So we're going to take the limit as x goes to 5 from the negative side, and the limit as x goes to 5 from the positive side of this function f of x. And remembering, we can use the graphical representation of this. So I'm going to go ahead and pull out the calculator. We're going to have 3, and we're going to divide it by the x minus 5. And looking at that graph, we see something that looks like this, and it comes out like this. So as we get closer to 5 from the negative side, we see that we go to a negative infinity. And from the positive side, we see that we have positive infinity. So it's going up like that. So since we have the limit as x goes to 5 from the positive and negative side as being an infinity, we know the proof, this is our proof, that x equals 5 is, so therefore x equals 5 is a vertical asymptote. In example 2, we have x squared minus 4 over x squared plus 4x plus 4. So here I'm going to go ahead and factor my numerator and my denominator so I can remove any holes that I might have. So here we're going to eliminate my x plus 2. That removes my removable discontinuity, or my hole. So now I'm going to be looking at x minus 2 over x plus 2. I'm going to set my denominator equal to 0, so I get x equals a negative 2. So now what I can do is go ahead and take the limit as x approaches -2 from the negative side, and the limit as x approaches -2 from the positive side. So again, I'm going to go to my calculator. I can go in and type in my x minus 2, and I'm going to divide that by my x plus 2. Graphing that, we have this graph that looks something like this. So again, there's our x equals -2. From the negative side, we see it goes to a positive infinity this time, and from the positive side, it goes to a negative infinity. So again, here's our proof. There's our justification. The limit as x goes to -2 from the positive and negative side goes to one of the infinities. So therefore, x equals -2 is a vertical asymptote. I have just one more example for us to look at today, and it's our old trig function, tangent. What a fun one there we look at. What do we do with tangent of x? Well, if we think about the graph of the tangent of x, we should remember, hopefully it comes up, it goes through the origin 0, 0, and we have these asymptotes on the sides, and then we come up and do it again, and we come up and do it again over here. Kind of repeats itself. It's very cyclical, we say. So what are these values here? We have -pi/2, and we have pi/2. So we know that we have a vertical asymptote through x equals pi/2. So we're looking at the limit as x approaches pi/2 from the negative side, and the limit as x approaches pi/2 from the positive side. Again, if you don't remember what that graph looked like, hopefully you do, but if you don't, you can use your calculator. Not a problem with that at this point. But eventually we're going to have to know what that graph looks like without a calculator. So from the negative side, as x approaches 2, it's going to a positive infinity, and a negative side is going to be a negative infinity. Likewise, we know that every pi/2 or plus pi units, there's going to be a vertical asymptote. So we know that x equals pi/2 plus or minus a pi, n, where n is an integer value, is a vertical asymptote. And that's going to define that vertical asymptote for us. And that's going to conclude our vertical asymptote section. Happy limiting.